All right, guys, so in one of the last videos that we covered, we went through and found a Thevenin equivalent circuit for a circuit that contained nothing but dependent sources. The same method of finding the open circuit voltage and then finding the short circuit current and then using a few extra equations, that same method can be applied to find the Thevenin equivalent circuit for a circuit that contains dependent sources as well. However, I really want to get very concrete and go through a particular example to show you how you can use these same concepts to find these Thevenin equivalents. So the next example here that we are going to cover is finding the Thevenin equivalent. My V is a little bit funky. Let's go ahead and erase that. With dependent sources. Now, the circuit that we're going to take a look at contains an independent voltage source, providing us with 24 volts. We then have a resistor here, an independent current source, providing us with 4 amps downward. There is one resistor there, and then we finally see our first terminal, terminal A. This bottom portion of the circuit is then complete with our terminal B there. And then we have our dependent source at the very top. This is a current source, providing us with the current 3Ix. Ix has been defined to flow down through this resistor in this direction. And then finally, this is the 2 ohm resistor and then the 8 ohm resistor. And the goal is to find the Thevenin equivalent circuit how about I spell that correctly? Equivalent with respect to terminals A and B. So we're looking in through these terminals and finding the equivalent, Thevenin equivalent with respect to that. Remember, our solution is going to be a voltage source that happens to be in series with a resistor. And we'll have the terminals A and B there like this. This is the Thevenin resistance. This is something that we're actually going to be looking for. And then we have our Thevenin voltage up here, and this is something that we're going to be looking for as well. And just like in the previous circuits, what we're going to do is we're actually going to consider first the open circuit, find the open circuit voltage, that will be our Thevenin voltage. We'll then consider the short circuit, find the short circuit current, and then the relationship between the Thevenin resistance, the open circuit voltage, and then the short circuit current is a simple one. It looks somewhat like Ohm's law. We can use that to find that final piece of the puzzle, the Thevenin resistance. Now remember, when you consider the open circuit and then you consider the short circuit, those are 2 separate circuits, right? And you can use any technique of circuit analysis that you want in order to solve for those parameters of interest. So you can use node voltage method, short mesh current method. You can use equivalent resistance, resistors in series and in parallel. Anything at your disposal, you can use. Right. So let's go and start with part number 1. And for this part, we're going to consider the open circuit. Why? This is going to be to find the open circuit voltage, and from theory, we know that this is the Thevenin voltage. So we're going to go back up to the circuit and then find that open circuit voltage. So I'm going to redraw that circuit. That circuit consists of my 24 volt source here. It is hooked up to a resistor there. It is then hooked up to a 4 amp current source here. We have another resistor there, terminal A. Then on the bottom here we have terminal B. At the top we have a dependent source. This is a current source providing us with 3Ix. And Ix is the current flowing down this way. This is an 8 ohm resistor, and finally this is a 2 ohm resistor. Now the open circuit voltage is the voltage between terminals A and B, like this, with that particular polarity. Now notice that that open circuit voltage is the same voltage applied across this 8 ohm resistor. So one of the things that I'm going to do is I'm going to use the node voltage method to set up a system of equations in order to find what that open circuit voltage is. Now, due to the fact that we have a dependent source here, remember, we're going to have to go back and take a look at what that dependent source actually depends on, and then write down an equation in terms of those node voltages in order to get that extra equation that we need to complete our system of equations, right? But we'll see how that works here in practice here in a second. So here I'm going to use the node voltage method to solve. Now, do I have to use the node voltage method? No. I can use any other method that I want. This is just my choice. So here I'm going to identify my nodes. There's one large node down here. I already know that I'm going to choose this as my ground. So that has a node voltage of 0 volts. There's one node there. And then there's one large node right there. I'm going to go ahead and call this node A. Right. Now, I'm not going to name the other nodes for reasons that will become apparent here in a second. Remember, the next step in using the node voltage method is we need to take a look at where our voltage sources are located, because every voltage source reduces the number of independent nodes by 1. There is a voltage source right there. That means that this node up here that I did not name does not have its own node voltage associated with it. This node voltage up here is actually fixed. When I go from the round node up to that node in question, I go through a voltage rise of 24 volts. So this is not independent, this is 24 volts. Similarly, notice that I don't need a separate variable name for the node voltage for this node. Why? Because this is already VOC. So here, the node voltage at this node, as opposed to calling it something like VA, well, it's already the VOC that I'm looking for. Now, I'm going to go ahead and use KCL at node A. And the convention that I'm using is that the sum of the currents flowing out of this node must add up to 0. So here, I have one current exiting this node going that way. That's 3Ix, so plus 3Ix. I have a current going from this node to that node out of node A. So that is plus VOC minus the 24 volts that it's going to, divided by the 2 ohm resistor that it's flowing through. I also have a current going down this way, and it's going out of that node, so I have plus 4 amps. And then I have a current going down that way out of node A. Now notice that I can actually use the node voltage VOC to write down what that term is, or I know that that current flowing out of there is Ix. So I'm going to simplify my life and just say plus Ix flowing out of that node. Those are the only components hooked up to node A. Those currents must add up to 0. I can rewrite this to put this into standard form. So first things first, I'm going to get rid of that fraction. So I'm going to multiply everything through by 2 and distribute. So here I have 6Ix plus VOC minus 24. The 2 times 4, that's plus 8, and then plus 2Ix, that's equal to 0. Let's keep VOC as the first term. So here I have VOC. I have a total of 8 IX's, one coming from that term, one coming from that one. If I add 8 and minus 24, that is minus 16. I can add that term to the opposite side at the expense of the minus sign, so this is plus 16. I'll call this equation 1. Now, I need, since this is an equation with two unknowns, I need one last equation in order to get the two equations to form my system of equations. And since this has a dependent source, this dependent source depends on Ix. So that last equation, I need to go back to where Ix has been defined, right here, and then use the node voltages to find and form an equation to get that value of Ix in equation form. So over here, I'm going to get a constraint equation by looking at where Ix is defined. Ix is defined right here. And in terms of that node voltages, Ix is going from the node A all the way down to the ground node flowing through the 8 ohm resistor. Therefore, I can say that Ix is equal to VOC minus the ground node, that's 0 volts, that is flowing through the 8 ohm resistor, so divided by 8. Or just very, very easily cleaning this up, I can get rid of the 0, so I have Ix is equal to VOC over 8. This is now my equation 2. Right? And I got that again by taking a look at where Ix happened to be defined. Let me add in the portions here that had been erased. So I have a system of two equations and two unknowns. Now you can use your calculator to solve the system, but this is a very simple system to solve. So I'm going to go ahead and use equation 2, and I'm going to directly plug it into equation 1. Just directly plug it in. So here I have VOC plus 8 times Ix right there. So I'm plugging that back in. So I have VOC divided by 8. All that has to equal 16 volts. Notice very nicely this 8 and that 8 cancel out very easily. I have 2 VOC is equal to 16, or VOC is equal to 8 volts. This is the first portion that I need to keep in my back pocket. This is equal to the Thevenin voltage. So I now know, in terms of my solution, that this right here is 8 volts. That's the same open circuit voltage that we just found in part 1. Now let's move on to part 2. And in part 2, I'm going to consider the short circuit. Why? Because I can find the short circuit current, and then I know that my Thevenin resistance is my open circuit voltage divided by my short circuit current. We found the first piece in the first part. I can then find my Thevenin resistance. That's the only piece that's missing. So here, let's redraw our circuit. So here I have my 24 volt source. This is hooked up to a resistor there, followed by a 4 amp current source here. This in turn is hooked up to a resistor there, and then we have our terminal A. This bottom portion of the circuit is then complete. At the very top, I have a dependent source. It is a current source. It is providing us with 3 Ix worth of current, and Ix has been defined to flow down this way. Lastly, this is a 2 ohm resistor, and this is an 8 ohm resistor. Now here comes the important part. I am then going to place a wire on the outside of terminals A and B, and there will be a short circuit current that flows out that way. Now, this is going to be a somewhat clever part, right? Suppose that we have, and this is just kind of make-believe, we know that there's going to be a current that's flowing out this way. Let me just call that current I. Now, notice that there's a node there. As that current enters in through that node, part of it's going to split off and go down this way, and part of it's going to split off and go down this way, right? However, notice that this has a resistance value of 8 ohms. This is a short circuit. So as that current enters into that node, all of that current I is going to go on the outside. Over here, none of it's going to go down this way through the 8 ohm resistor. That's what a short circuit is, right? It essentially takes all of that current. That means because of the short circuit, so because of the short circuit, Ix is 0, right? That means also that 3Ix provided by the dependent source is 0 as well. Now, the fact that this up here is providing us with 0 amps, right, means that this dependent source, because it is a current source, that dependent current source can be replaced with an open circuit. So here, because of the current-controlled current source giving us 0 current, we replace it with an open circuit. That means that this resistor, really, when we rewrite the equivalent circuit, it's as if it's not playing any role, and this dependent source up here, it's as if it's not playing any role whatsoever as well. So let me rewrite the circuit. That circuit does contain a 24-volt source. There is a 2 ohm resistor there. There is a 4 amp source there. That 8 ohm resistor is not playing any role in the circuit whatsoever. Neither is the dependent technique of circuit analysis that we want in order to solve this problem. Now, what I'm going to do is I'm going to go ahead and take a look at these 2 nodes here. Right. Notice that one of the things that I have in the box is I have a voltage source that happens to be in series with a resistor. So this is a perfect candidate to do a source transformation. Right. So here, with respect to, let me call this node C and D, I'm going to do a source transformation here. Which means that this voltage source that's in series with this resistor, I can replace with a current source that happens to be in parallel with a resistor. And this is with respect to the terminals C and D. So I have those terminals there, I'm respecting them, I'm keeping them there. This must be the 2 ohm resistor, and the direction of the current must be going in this direction, upward. Now, the amount of current that this is providing us with under the source transformation, well, it must be the 24 volts divided by the 2 ohm resistor. This gives us a total of 12 amps. Therefore, this must be 12 amps, not volts, 12 amps. Right. I still have, to the right of this, I still have my 4 amp source there, like this, and I still have my short circuit like that. Now, if you take a look at the resulting circuit, we have these 3 elements and even the short circuit, they are all in parallel with respect to one another. So I can go ahead and add this 12 amp source to the 4 amp source, and I'm going to place them on this side. So here, since they are in opposite directions, 12 amps is going up, 4 amps is going down, you can add those parallel sources together to give us a net 12 minus 4 amps. That's 8 amps going this way. I still have my 2 ohm resistor here. I still have my short circuit current there, like this. And now we're going to use the same argument that we used before. I know that into this junction, we have a total of 8 amps flowing into that junction, right? Now, this is a current divider. Some of that current would go down this way, some of that current would go down that way, right? But there's a short circuit there. That means that 0 current goes down that way, and the entire 8 amps must flow through the short circuit like this. So here, without any more analysis, I know that my short circuit current is now 8 amps. This is important. Let's box that. And if you use any other technique of circuit analysis to find that short circuit current, you will find exactly the same thing that I'm saying now. Right? So now we can go back to the relationship that we had before. The Thevenin resistance is equal to the open circuit voltage divided by the short circuit current. The open circuit voltage we found previously to be 8 volts. The short circuit current we now found to be 8 amps, therefore my Thevenin resistance is 1 ohm. This was the last, again, piece of the puzzle that we needed to find our Thevenin equivalent. Right? So we can then now go all the way back to our solution. This is 1 ohm, and let's just write it out very, very, very cleanly. Our solution to finding the Thevenin equivalent circuit with a dependent source consists of a voltage source, where this is the Thevenin voltage, this is 8 volts. Thevenin resistance, we just found this to be 1 ohm. We have our terminals A and B. This is what we wanted. So once again, hooray, we solved the problem. Right. Notice that we can use the same techniques that we used previously in finding the Thevenin equivalent with a circuit with only independent sources. We can still tackle circuits that contain dependent sources. However, we have to take a look at where the dependent source, what that depends on, and then write down an extra constraint equation in order to complete our system of equations to solve for whatever it is that we need to solve for. Thank you for watching, and we'll continue along with these videos some other time.